All right, hi folks, this is Larry Maslino. I wanted to record a short video here and walk through a few of the homework problems from Module 5. I'll split this up into a Part 1, Part 2 video. So let me do a few examples to help you get started. So I'm here looking at number 1, and it says, suppose that a dimension x and the area of this figure are differentiable functions of t. Write an equation that relates dA dt to dx dt. So imagine, x is the, some dimension that's changing over time. Well, if x changes over time, the area of this shape will change over time. And so they're asking us to come up with an expression here for dA dt. Well, you can think of this in terms of the chain rule. So we could think of dA dt as being dx, dA dx, dx dt. Because they're asking us to figure out the relationship with regards to dx dt. All right, well, let's work out dA dx. That's just the derivative of a with respect to x. Well, if we take the derivative of a with respect to x, I'm going to use the power rule for derivatives. Let me remind you about that. If you want to take the derivative of x to an exponent, the rule is you take the exponent and bring it down in front of x as a multiplier. And then on x, you make the new exponent 1 less than the exponent you started with. So in our example, this 8 is a constant. So I'm just going to leave that alone. Now I'm going to take the derivative of x to the 2 using this power rule that I just mentioned. Well, that 2 comes down in front as a multiplier of x. The new exponent is 1 less than you started with. 2 subtract 1 is a 1, so the new exponent is 1. dx dt, they didn't give us an expression for x here, so we really can't work out dx dt. We're just going to bring it down with us. And I'm noticing in the answer, they left dx dt intact here. So they're really asking us to put in the answer box what's in front of dx dt here, which for us, of course, is just 16x. So the answer here is going to be a 16x for the answer box. Okay? All right, let's do another quick example here. I guess we could go to number 2 maybe. All right, so this one says x and y are both functions of t, and it says y equals x to the third plus 2. And it also says when x equals 1, dx dt is equal to 4. And the question here is find dy dt. All right, well, why don't we start out thinking about this as dy dt. That's what they're asking us for. And I'm going to take the derivative of this function, but I got to remember that x is a function of t. So when I take this derivative of x to the third, that's 3x squared. But I got to keep in mind the chain rule that says we need dx dt as well. When you go to take the derivative of this 2, remember the derivative of constant is 0. So the derivative of that 2 really is a 0. All right, well, let's work it out now. They want dy dt, but they're telling us x is 1. So I'm going to replace this x with a 1. And they gave us dx dt when x equal 1. They said that dx dt is 4, so that's a 4. So this is just going to be 3 times 1 times 4, or 12. So the answer here is just 12. All right, let's do another example here. I want to do an example related to what's called related rates. And related rates are when two quantities are changing in regards to each other. Let me give you a couple of examples of related rates. Let's say there's an oil spill that's circular. And so here's the radius of a circle. Well, over time, this oil spill might get bigger. So R is going to get bigger. But also the area of the circle is getting bigger as well. So the radius here, the rate of change of the radius is going to be related to the rate of the change of area. So we call those related rates. In this example, we're looking at the Y. So it's a ladder that's slipping down the wall. So this Y component is the rate of change there is going to be related to the rate of change of this X. And another part of this question is going to ask us the rate of change of this angle theta. All right, well, let's start out with the diagram they're giving us. And so they're telling us this ladder is 13 feet. All right, of course, this ladder, the length of the ladder is not going to change. That's always going to be 13 feet. It says the base starts to slide away. So you can see they're telling you the base is sliding over to the right here. At the time the base is 12 feet from the house, let me draw a little diagram here to show this. So they're telling us that this ladder is in a position where the base is 12 feet from the side of the house. The base is moving away at a rate of 10 feet per second. So this 10 feet per second moving this way. And remember, the ladder is 13 feet. That doesn't change. Now, as this red dot moves to the right, this blue dot is going to be moving down. Remember, this ladder is kind of sliding downwards. What is the rate of change of the height of the ladder? And of course, we'll label this as X and Y. So really, part A is asking us find dy dt. That would be the rate of change of Y over time. All right, well, let's see if we can set up some kind of a relationship here. Well, the obvious relationship here for part A is going to be use the Pythagorean theorem because it's a right triangle. So if I call this X and I call this Y, I can write that X squared plus Y squared equals 13 squared. All right, well, I'm going to take the derivative of both sides here. I got to take into account the chain rule because both X and Y are changing as a function of time. So when I take the derivative here, I can write this as the derivative of X squared is 2X dx dt plus 2Y dy dt. Now I'm going to set that equal to 0 because this is a constant on the right side. When I take the derivative of 13 squared, that's 0. All right, let's see what quantities we know. At this point in time, they're telling us that X equals 12. We also know that dx dt, that's the rate of change of the ladder in the X direction, that's 10. They told us that. The other item we'd like to know is what is this Y value at this instant in time? Well, to find the Y value, we can just set up a little equation with the Pythagorean theorem. We could say X squared plus Y squared equals 13 squared. The X is 12. The Y is unknown, so we can use this to figure out the value of Y. So this is 144 plus Y squared equals 169. I'm going to subtract 144 from both sides here. And that's going to get me Y squared equals, what is this? 25. Yep. So Y is 5. So we know this Y dimension is 5. All right, let me take this equation and plug in everything we know. So let me mark here Y equals 5. So it turns out we know X, we know dx dt, we know Y. Dy dt is the only unknown, which is the quantity we're trying to figure out here in part A. So let's go plug in. We have 2 times X, that's 2 times 12. Now we need dx dt, but that's a 10. Plus 2 times Y. The Y value we figured out is 5. dy dt is the unknown, and this is equal to 0. All right, let's see here. This is 240 plus 10 dy dt equals 0. Subtract 240 from both sides. That means we have 10 dy dt equals negative 240. Divide both sides by 10, so it looks like dy dt equals negative 24. The negative sign is telling us that the direction is downward. So part A, we're coming up with that the rate of change of the ladder is moving downwards at 24 feet per second. All right, let's go to part B of this example. Part B says, how about the area? Well, let me draw my little diagram again. Here was our x, y, 13. Here's the angle theta they're talking about. Well, what is the area of this triangle? Well, the area of a triangle is just 1/2 base times height. Well, that's going to be 1/2 x times y. But remember, x and y are changing as a function of time. So let me use the product rule, because we want to know what is dA, the derivative of a here. We're going to take derivatives, all right? So this is going to be, let's use the product rule. I'll call this the f function. I'll call this the g function. So I'm going to leave the f function alone and take the derivative of y. The derivative of y is really 1, but I have to include a dy dt term. All right, now plus, now I'm going to take the derivative of y, excuse me, I'm going to leave y alone and take the derivative of x. Well, the derivative of 1/2 x. So that's going to be 1/2. The derivative of x is 1, but I got to include a dx dt term. All right. And remember, in this case, we're trying to find this rate of change of a. That's the unknown quantity. Let's see if we have everything we need to plug in. We know the x value was, what was the x value again? 12. dx dt, that was given to us as 10. We figured out the y value a few minutes ago. It was 5. We also figured out dy dt, that was negative 24. That was from part A of the question. So I think we have everything we need to plug in here. So it's going to be 1/2 times the x value of 12. dy dt is negative 24. Plus the y value is 5. And dx dt was 10. And if you work this out on your calculator, you should get the answer negative 119. So what's telling us is the area is getting smaller over time. The area is decreasing. That makes sense because as this ladder slips down, the area is going to be getting smaller and smaller over time. All right, let's do one more part, part C. Part C is a little tricky because it involves some trig calculations. So now they're asking us, at what rate is the angle changing? Well, they're really asking us here to find d theta dt. By the way, folks, remember, anytime they say rate means a quantity is changing over time. You know, if you're on the highway, your rate of speed is 60 miles per hour. So anytime the word rate is mentioned, you know it's a change over time. All right, well, let's look at this diagram again. Let me draw it here. Here's the angle theta. And this was 12, and this is 5, and this is 13. All right, we know this point is going down at negative 24 feet per second, and we know this point is moving to the right at 10 feet per second. All right, how about if we start out writing an equation for theta? And maybe this is y and this is x. How about if we write cosine theta? So cosine theta is equal to x over 13, right? X over the length. I could use sine. I could use tangent. It's up to you. All right, let me take the derivative of both sides of this equation. The derivative of cosine is negative sine, but I got to take into account that angle is changing over time, so I'm going to include d theta dt. On the right side, we have 1 over 13. The derivative of x is 1, but I got to include a dx dt because that x value is changing over time. All right, let's see if we can plug in here. What is the sine of theta at this instant from my diagram? Well, sine is opposite over hypotenuse. So the sine here is 5 over 13. And that's equal to 1 over 13. dx dt we know is 10. All right, let me solve this equation. I'm going to multiply both sides of this equation by 13 because that'll get rid of the denominators here. So multiply both sides by 13, cancel out the denominators. It looks like we have negative 5 d theta dt equals 10. But we want to solve for d theta dt. So we could just divide both sides by negative 5. So d theta dt is just negative 2. The reason it's negative is that angle is decreasing over time, and it's getting smaller by negative 2 radians per second. All right, folks, hope this is helpful as you're getting started here in the Module 5 homework. I will also do a part 2 of this video to do some additional problems as well.